Hey class, good afternoon or morning, whatever you're watching this. Today we are going to talk about significant figures. We're in chapter 2, section 3, and we're going to go on to Sig Figs. So when we talk about significant figures, it's really looking at numbers and just saying what numbers actually have a value. So I use an example of this. Let's say in your bank account, you have $999. And let's say your parents come home and they say, hey, son, how much money do you have in your bank account? And you tell them $1,000. Now, did you lie to your parents because you told them $1,000? Well, not really. It just depends on how accurate you were being with your parents. When we look at the first number, we notice that there are 5 places where we accurately measured the amount. 1, 2, 3, 4, 5. So that would mean there are 5 significant figures. But when I talked about the word 1,000 or the number 1,000, I only gave them one significant figure. One significant figure. And so this is the basis of the difference between significant figures and why they matter. It gives us an example of how accurate we are being when we take a measurement. They might have the same value, but right here it shows me I am much more accurate in the numbers I'm using opposed to 1,000 where I'm not as accurate. And so here we go. We will do measurements in chemistry all the time. We will use a meter stick. We can use a decameter. We can use centimeters, and we can use millimeters. And when we learn to do measurements in chemistry, we have to learn how to accurately read those numbers and tell us how accurate the number actually is. So here's an example. Pretend that this is a centimeter. Every mark is 1 centimeter. So if you look at the measurement, you should be able to tell me what the measurement is on this scale. Now, when we take measurements, we are allowed to estimate the last digit. And so here you should see that you would have 4.5 centimeters as your answer for how long this green line was. Now, if we look into the next slide, you will see that now my ruler has markings for every millimeter. So what would be the measurement for this? Well, here you would see that I know for sure I'm at 4 centimeters. I also know I'm at 4.1, 4.2, 4.3, 4.4, 4.5. So I know for sure that I'm at least at 4.5. But because we're allowed to estimate that last digit, I would answer this as this green line is 4.55 centimeters long. And so we see that the more markings we have, the better our estimate is. And so let's look about it in reverse. I have 4 rulers here, or rulers here. This is a meter stick. This is a decimeter. This will serve as a centimeter, and this will serve as a millimeter. Which one of these rulers could serve and give me the accuracy of 2 decimal places? Well, the answer would be my millimeters. Just like we saw on the last slide, that when I have the ability to measure to the millimeters and I have those markings, I can get 2 decimal places in my reading. And so I have 142.15 centimeters. If I get the next number, which ruler would I use to get that accurate a number? And the answer for that one would be the decimeter. The decimeter does not have the ability to show, decimal places on the centimeter level. But it can get me to a place where if I measured my arms all the way across, and at the very end, if I got to 140 centimeters, I could estimate that last place as a 2, and I could say I have 142 centimeters according to the decimeter. And then the last one we see is 140. You need to notice that this 0 is not significant. If it was significant, there would be a decimal here. but it is not. So we are not certain here. We are certain about this number, but we are uncertain about this number. So if I had a meter stick, and again, imagine this meter stick did not have any markings inside the lines. It just said 0. It said 0 to 100 centimeters. 0 to 100 centimeters. And if I went to measure my arm, and when I got to the end, if I didn't have these markings to tell me, I would have to estimate that tens placeholder. And I could estimate it to be at 40, and I could say I have 140 centimeters. Now, this is just some rough examples to explain to you why we might have different levels of accuracy in our numbers. So the question is, zeros. Do zeros have significance? They do and they don't. So what we need to do is we need to look at a set of rules to decide when zeros count and when they don't as significant figures. So take a second, pause the video, and read Table 5 on page 47 to look at the 4 rules of when zeros are considered significant or not. Here are a few examples that you can see. For example, right here, according to my rules, zeros after a decimal with whole numbers does count as significant. Zeros in the middle of numbers is significant because this was a measured value. Likewise, this was a measured value. But if I look at the number 4,050, this 0 would not be significant. Again, I had to guesstimate on this number, and I don't know if this was a true measurement. If I had a decimal here, then yes, this 0 would be significant. However, this 0 is significant because it is in between 2 whole numbers. Let's look at number 3. Number 3, you have 0.450. The 0 to the left of the decimal is not significant. The 0 to the right is, because again, it is showing me how accurate I measured when it came to my decimal places. One other way to think about it when you get into decimals is to think about it in terms of scientific notation. I would write this number as 4.50 times 10 to the negative 1 grams in scientific notation. That shows me that every 0 to the left of these numbers, like in example 5, are not significant. They're just placeholders, like this number is a placeholder. Now look at number 4. To quickly go through here, this 0 is not significant. This 0 is significant, this 0 is significant, and this 0 is significant because they are all between other measured values. And finally, these 2 zeros would not be significant, but the rest of the zeros would be significant based upon those rules. We will practice these with worksheets, and hopefully you will get familiar with them. So right now, just breathe, take in the rules, and the more we use it, we'll be off. So what we see here is that only measurements have significant figures, things that I can measure, whether I measure it with a ruler or I measure it with a graduated cylinder. Same case, if I measure with a graduated cylinder, I'm allowed to estimate that last digit. So if I had water filled up to this line, I would give this a measurement of 35.5 milliliters. And since it's a measurement, I have to have Sig Figs included. Other numbers don't have significant figures. More like they have infinite significant figures. And what that means is when we have an exact quantity, that is an absolute number. So the significance goes on forever. Think of it in terms of a dozen. A dozen is exactly 12. You cannot have a dozen of something and have 12.1 or 11.59. No, dozen is an exact quantity. Just like our conversion factors. Our conversion factors of 100 centimeters equal to a meter is a definition. It's an exact measurement. So the significance of that number goes on forever. So you could in some way say 100.0000000 infinitely 0 centimeters equals 1 meter because it's an exact definition. So when we look at a problem like this, 50 only has one significant figure, being the 5. My 0 is not significant. But what if I wanted to make that a significant number? Well, I have 2 options. I could put a decimal here, and that would show 50 as significant, or I could turn it into scientific notation, where I would write as 5.0